Okay, so if we go out and we find our planet around a star, the first thing we'll say is, okay, how do we tell which one is the habitable one? We've gone through those characteristics, but how are we actually going to do it? So as I mentioned before, and this is kind of a summary of what we've talked about, first we'll look at its neighborhood. You know, what's its parent star like? Has it got a good parent star? Are there other planets in this system that could be a bit of a problem? For example, a large Jovian, a large Jupiter-sized planet careening through the solar system on a highly elliptical orbit. Don't laugh, they occur, and in fact they occur more often than nice, well-behaved circular Jovians, as we've discovered looking out at other systems. So having one of those in your solar system would be very bad if you were trying to be a little habitable planet in the inner solar system, inner planetary system. The other thing we look at are the mass and orbital parameters of the planet itself. Is it the right size? Is it a terrestrial mass? Is it in the habitable zone? Then we look at what we call its photometric characteristics. Photometric just means to measure light. So again, we look at the light coming from that planet. We determine its brightness compared with its distance and try and work out how much light it's reflecting to tell us whether it's covered with clouds or not. We look at its color. We look at whether it changes with time. Does the brightness or the color change with time? Anything that could indicate clouds going round or, you know, moss growing up over one side of the hemisphere and back. Anything like that that would give us further evidence that this thing is terrestrial, that it has clouds, and that it has a surface that perhaps changes. And then we pull out the big guns, which is the spectra. So once we find this planet, if it's bright enough, we'll be able to break that light up into its constituent colors. And we will look for things that I showed you before, like carbon dioxide and water vapor. The carbon dioxide tells us that we probably have a terrestrial planet. Jovian planets don't tend to build up large amounts of carbon dioxide because of all the hydrogen in them. It would tend to react and take them away. So if you see CO2 on a planet, chances are it is actually terrestrial. The other thing we look for is, again, the water vapor to tell us whether it's got liquid water on its surface. And we'll also look for whether or not this planet has a UV shield. That's another thing that's very important for a habitable planet. Does it have something in its upper atmosphere, like an ozone layer, that stops damaging UV from getting to the surface? And it turns out that in the spectra of planets, we can also see ozone. And then we'll look for clouds and other greenhouse gases that might be in there. And the greenhouse gases are very, very important because even though you can take the temperature of a planet, and we do this all the time with planets in our own solar system by looking at what we call infrared radiation coming from those planets, even though you can take its temperature, you might get it wrong, because the only temperature you can take is the temperature it's willing to let you take, which is this temperature of the emitting layer. So if your planet's completely covered with clouds, like Venus, for example, Venus returns a very cold temperature when you look at it, because you're actually looking at a region above the clouds when you take its temperature. But in actual fact, Venus, of course, is extremely hot on the surface. So even though you can take the temperature of the planet, you may not get the surface temperature. But if you can do a census of the greenhouse gases in the atmosphere and get some idea of the composition and the mass of that atmosphere, you can then use our next tool in this battle, which are the models. So you can take that information that you've gleaned from telescopes and observing and combine it all together and try and determine the surface temperature via modeling by knowing how much greenhouse gases there are in the atmosphere. And a little greenhouse warming is a wonderful thing. And it turns out for the Earth, we have about 32 Celsius of greenhouse warming, which takes us from frozen to very nice, thank you very much. So that's important. That's what our atmosphere does for us. Venus, on the other hand, as I said, if you look at its effective temperature, it's very cold. But it turns out its surface temperature is mind-bogglingly hot, and it undergoes about 513 Celsius of greenhouse warming, so that's not a good thing. Mars, on the other hand, it tries really hard, but it can only manage 5 Celsius of greenhouse warming. And so it just goes from really, really frozen to just really frozen. So it tries, but very thin atmosphere. It doesn't help. But that's another thing about habitability. Your atmosphere needs to be thick enough for you to get your surface temperature up to something decent. So the point here is that a planet's greenhouse effect is at least as important in determining the planet's surface temperature as its distance from the star. So you go for the distance first, but you also better take a census of what gases are in the atmosphere and how dense that atmosphere is to work out what the surface temperature is. So we have so many planets out there. I think there's about 211 now known. It could have changed since I wrote this slide this afternoon, though. But there's one problem with all of these planets that we have found so far. Sorry, not all of them, most of them. They're too big. These planets we have found are mostly gas giant planets. So these small, rocky, Earth-like planets, the terrestrial planets that we want to find around good parent stars, are still very difficult to find. And I gave something like this talk a couple of years ago, and then I was able to say we don't have any at all. But now in the last couple of years, thanks in part to something called the microlensing technique, we've actually found a handful of planets that are less than 10 Earth masses. So these are our best candidates for being these rocky worlds, and it's amazing we've been able to find them so far. And some of you may have heard of the recent discovery of Gliese 581c, which came out, I think, last week or this week, I can't remember, last week. And that planet is only about 5 Earth masses. It's one of the smallest planets we've found so far. And at the time of the press release, they were saying that it was, in fact, in the habitable zone of its parent star. And that was hugely exciting. This was the first potentially habitable planet that we had found, and in my own lifetime. So that was very exciting. Unfortunately, my team went back and actually recalculated the habitable zone. And what we discovered is that this thing is probably not in the habitable zone. It's a little too close. So this thing is not a super Earth, it's a super Venus. Good. I'd be happy with that. That's okay. It's something to start with. But it turns out its brother, which is Gliese 581d, which is another planet in that system that's about 7 to 8 Earth masses, that one potentially is in the habitable zone on the other edge of it, on the outer edge of the habitable zone. And given that it's a very large planet and may have a very dense atmosphere, that one could, in fact, be habitable. So what you gain on the roundabouts, you lose on the swings kind of thing. This one may not be habitable. The other one in the system might be, though. So how can we tell if a planet is inhabited, especially from a huge distance? Well, if it's got aliens on it, it's easy because they actually tell us that they're there. They can say hello to the universe and they can tell us. But what you have to remember is that our planet has been able to say hello to the universe only for the last 100 years or so. So for the previous 4.6 billion years, we didn't say a whole lot to the universe. So that would be the easy way of doing it. But again, it's maybe statistically not that likely. What is statistically more likely? This stuff. These are stromatolites. These are microbial mat communities. I think this was one is in a bay in Australia. But these sorts of things are believed to have been the dominant life on the Earth for maybe 2 billion years or so. So statistically, when we go out and look at planets, these may be the things we're more likely to see. And what do you hear from them? Not a lot, okay? So when you're looking for life on most planets out there, you're going to have to be cleverer than just simply listening. So our best chance then is, as I've mentioned already, is to look for global changes in the atmosphere and surface of the planet thanks to life. Now it turns out that life actually leaves its footprint on this planet in a big way, which is great. So what we're looking for now are these astronomical biosignatures, not the in situ I have the rock in my hand biosignatures, but biosignatures that can only be seen by using either an orbiting spacecraft or a telescope looking out at a distant planet. So these biosignatures are global scale photometric spectral or temporal features, so that's, counting the light, breaking it up into its constituent colors, or time-varying features indicative of life. And if you look at the Earth, there are 3 major types of biosignatures that I can think of. First of all, there are things in the planet's atmosphere, there are things on the planet's surface, and there are ways that the planet's appearance, both its surface and its atmosphere, change over time that tell us that life is there. But the other thing we have to remember before we go rushing off and saying, oh, we'll look for oxygen, for example, is that biosignatures must always be identified in the context of the planetary environment you find them in. Otherwise, you'll get fooled. And the classic example is methane. On the Earth, methane is a biosignature. It's produced in rice paddies. It's produced by cows. It has a seasonal cycle. And it's seen in the presence of huge amounts of oxygen. And chemically, that shouldn't happen. Usually oxygen and methane like to destroy each other via various circuitous pathways. So the fact that they're both there means that they're both being produced at the surface of the planet. And the most likely source of both of them is life. But on Titan, there's methane in Titan's atmosphere, but it's just there. That's part of its atmosphere. And you can tell that by looking at the other constituents in Titan's atmosphere. So in that case, Titan's methane is just part of its atmosphere, but on the Earth, it's actually a sign of life. So if we go through the signs of life in detail, signs of life in the atmosphere, this green squiggly line here is what the Earth looks like if you were able to see in the infrared. So these are the infrared wavelengths of light, and this is essentially how much radiation is coming off the planet. So we're looking in heat energy here. And what you see in this curve is that there's this very obvious feature here. There's this kind of dippy thing here, and if you look very carefully, you can see this little tiny spike here. So what we're actually seeing there are ozone And down here, much harder to see methane. Okay, so as I said, oxygen and methane together are a sign of life. But it turns out that ozone is produced from oxygen. And if you see a lot of ozone, chances are you have a lot of oxygen. And so that's also a proxy for life. And this feature over here, that's good old carbon dioxide.